Okay, second last module on the integral. Okay, so this is kind of leading up to this, or what we've done before. So I want to introduce the idea of the integral. And so what we've been doing the last week or so is we've been trying to get some quantity, and the way that we've been getting at that is by making better and better estimates by sampling more frequently. So we've been doing Riemann sums with more terms and shorter subintervals. Okay, so this process of refining those Riemann sums gives us a mathematical object called the integral. Okay, so by refining, we're taking a limit, right? We're doing something, we're doing more work, and we're seeing stabilization. This is exactly kind of like what we did with the derivative when we looked at difference quotients and we made better and better estimates by taking shorter subintervals of the difference quotient. Okay, so let's look at square root of x cubed plus 1 on the interval 1, 3. And the important lesson here is it doesn't matter how we sample our subintervals, we're going to get the same answer. Okay, so I'm going to start off by taking 8 subintervals on 1, 3. So that means each is going to be a quarter. So my points, my grid is like 1, 1 1/4, 1 1/2, all the way up to 3. And in the left sum, I'm going to sample the leftmost point in each subinterval. So that means I'm going to sample at the points 1, 1 1/4, 1 1/2, all the way up to 2 3/4. Okay. In the right sum, I'm going to sample the right end of each subinterval. So I'm going to start at 1 1/4 and go all the way up to 3. And in the midpoint sum, I'm going to use the midpoints of each interval. And so I'm going to start at 1 1/8 and go all the way up to 2 7/8. Okay, and so when I do that, I get some answers. Okay, so it doesn't seem that great answers, but you know, we're only doing 8 subintervals. There's like, seems to be like around 0.6 between the left sum and the midpoint sum, and another 0.6 between that and the right sum. Okay, so we know what to do to get better answers. We refine things. So I'm going to take 64 points. So that means delta x is 2 1/64 is 1/32. Right? And when I do that, I'm happier now because my 3 answers are closer together, and it's making me believe that maybe there is something that it's converging to. Okay, so I try 512 subintervals. So each subinterval is 1 on 256. And even better, okay? So they seem to be around 0.007, something like that, between each one. And then for the final one, I'm going to take 4,096 points. And when I do that, I'm really, really happy, right? We seem to be getting that there is an answer. Okay, so what do we notice about this? Okay, so all 3 methods seem to be converging to the same limit. That's the important lesson. So no matter how we choose our sampling points, we're going to get there. But if you look at it, the midpoint sum is way, way faster, right? With the left sum and the right sum, we had to use like 4,096 subintervals to get a better answer for the midpoint sum for 8 subintervals. Okay, so we can be really confident that the midpoint sum there is giving us really good answers, and it's hardly moved at all when we went from 512 to 4,096. Okay, so we're seeing that there is a single number that all these Riemann sums are converged to, And so this is how we write it. There's that integral sign, which is like an elongated S. We put 1 and 3 to show that we're doing the interval 1 to 3. Square root of 1 plus x cubed, that's our function that we're taking the Riemann sum of, and our answer is 6.229959. And we're really confident in that based upon the table that I've got there. So, definition. Suppose all the Riemann sums for a function on an interval converge to a single number when the lengths of the sub-intervals are made smaller and smaller. Then we say the function is integrable, and we call the number the integral of fx on a, b, and we write it like that. And we call the function fx the integrand. Okay, so I notice that I use the word suppose. We remembered when we look at derivatives that not all functions have a derivative. Like, for example, if you have a corner, then it won't have a derivative at that corner. So an example of a function without an integral is this weird function here, which is equal to 0 if x is rational and 1 if x is irrational. And hopefully you can see that if you try to integrate that on 0 to 1, if you sample all rational points, the answer is going to be 0. If you sample only irrational points, the answer is going to be 1. And it's going to depend upon whether you choose rational or irrational points. And so you can get any number between 0 and 1. And so that doesn't make sense. So we just say there's no integral for that. Units for the integral are the product of the units for f times the units of x. That's different, right, from the derivative. So the units of the derivative, dy dx, are the units of fx divided by the units of x. So that's a per, something per. So that's how you know you've got a derivative. You know you've got an integral when you've got like a product. That integral sign is just an old way of writing S. So like sigma, it stands for sum. And so kind of way to think about integrals, it's a sum of all these products, f of x times dx. So fx is the height of these rectangles and dx are these infinitesimally small widths of our rectangles. And this process, what we're doing is called integration. So we've seen examples over the last week or so. So for example, when we looked at energy consumption, the basic relationship is energy equals power times time. That told us that, you know, Riemann sum was a good thing, so we could estimate it by a Riemann sum of rectangles of height, the power at a time times a width, and the units are megawatt hours, right? Because megawatts was the power units and hours were the time units. And if we refine the sums, we get an integral, and we get that the energy equals that integral between 0 and 24, because we're doing it over a 24-hour period of the power with respect to time. So we have that energy is the integral of power over time. And likewise, we've seen that distance is the integral of velocity over time, work is the integral of force over distance, and volume is the integral of area over distance. What about area? Okay. We've seen that how area is the integral of height over width. However, we get this strange little technicality happening. So suppose we try to compute the integral of x times cosine x over interval 2, 3. And we do that and we get a negative answer. You know, we do the Riemann sums and they converge to a negative answer. And this looks strange at first until we actually graph the function and we see that x cosine x is negative between 2 and 3. Okay, so the heights of those rectangles are negative, right? Because we're taking fx. So we've got to refine what we mean by integral as an area. And the simple thing is that it's the signed area between the graph of the function and the x-axis. By signed area, I mean that it counts as positive if it's above the x-axis, and it counts as negative if it's below the x-axis. So look at this picture here. We've got a function f of x between a and b. We've got 3 regions, 2 above and 1 below. Okay, if the area of those 3 regions going left to right are 2, 3, and 2, what is that integral equal to? Okay, so some notes then. Integration is nice and linear, right? So the integral of a sum is the sum of the integrals, just like the derivative of a sum is the sum of the derivatives. And we can see that, right? Because when we do the Riemann sum, if we've got height of our rectangle is f plus g, we can have a rectangle of height f, we can put it on top of a rectangle of height g, and then we can sort of break it up into 2 different Riemann sums. And so likewise, the integral of a difference is the difference of the integrals. Similarly, if we have a constant multiple times f, the integral of a constant multiple is a constant multiple of the integral. And again, that's because we look at the rectangles, we write it as a Riemann sum, we can pull out that constant from the sum. Okay. Other points that you should notice because of sign area, if we have a function which dominates another function, so g of x is always bigger than or equal to f of x on some interval, then the integral is going to be bigger than the integral of f. The integral of g is going to be bigger than the integral of f, right? Because everywhere the Riemann sum, the rectangles of g tower over the rectangles of f. So when we add those up, we're going to get that sum is going to be bigger than the sum of the smaller ones. There's another way we can do it. So let's say we have 3 points A, B, and C, right? The integral between A and C is going to be the integral between A and B and the integral between B and C. And again, it's obvious because you just take the Riemann sums and you know, you can just split the sum in 2 and the 2 sums become 2 integrals. Another nice thing is that we can think of integrals as kind of adding up, so we can do averages, right? So this is nice because this tells us a way to how we can get an average of an infinite number of things, right? Because typically when you do an average of an infinite number of things, you've got an infinite sum divided by an infinite sum, so it doesn't make sense. But it does when we can think of it as integrals, right? So the average value on interval AB is the integral divided by B minus A. And one way to think about this is, you know, you have your function on interval AB, you come along with a bulldozer and you move that area over to make you flatten it out to just make a rectangle, right? And the height of that rectangle is going to be the average value, right? So the rectangle is going to have area B minus A times the average value, and that B minus A times the average value is going to equal the integral. Well, if you just solve for the average value, you get that relationship right there. So your second question is, on this previous slide, if A equals 1 and B equals 4, what is the average value of that function on that interval 1, 4? Okay, and that does it for today.